Hello, long time no see, and welcome back to Dr. S's Random Math Lair. Today's video deals with a concept from single variable differential calculus known as the derivative, in the form of problem 10. This is often studied at the high school senior or college freshman level. In some previous videos, we briefly touched on this topic, but never really gave a formal definition of the derivative and how to compute it. This video intends to do exactly that, including where this concept originally came from, a few applications of it in math and the real world, some historical context related to it, and how it has developed and evolved into what it is today. A list of all the references, images, and online resources used in the making of this video will be mentioned towards the end of this video, and in the description below. Here's the statement for problem 10. In part A, use the difference quotient definition of the derivative to show that the derivative of the natural exponential function, e to the power x, is itself, keeping in mind the infinite power series representation of this function about 0. In part B, find the derivative of f of x equal to 1/3 x cubed, plus 1/2 x squared, plus x. In part C, using the quotient rule, calculate the derivative of g of x equal to 2x cubed minus 3, all over x plus 2, where x does not equal -2. Finally, in part D, using the chain rule, calculate the derivative of h of x equal to the square root of 1 minus x cubed, where x is less than or equal to 1. The concept of the derivative is studied in differential calculus, and basically, the derivative of a function is its rate of change. We briefly talked about it in the videos for problems 1, 2, 3, 5, and 8. Now, the original idea of the derivative comes from the tangent line problem, using the concept of limits. The tangent line problem asks, what is the slope of the line tangent to the point P, with coordinates say, x0, f of x0, on the curve represented by y equal to f of x? To answer this question, first, we find the slope of the secant line passing through P and another point Q, with coordinates x0 plus delta x, f of x0 plus delta x. Note that delta x refers to the horizontal change in x, as we traverse from P to Q along the secant line, shown in figure 1. In fact, delta x can also be written as the difference x0 plus delta x, minus x0. Likewise, the vertical change in y, or delta y, is the difference f of x0 plus delta x, minus f of x0. Thus, we have that the slope of the secant line being considered is equal to the ratio of delta y to delta x, which equals f of x0 plus delta x, minus f of x0, all over delta x. The right-hand side of the above equation is called a difference quotient. It remains to determine the slope of the tangent line passing through the point P, which we shall do next. Continuing with our discussion of the tangent line problem, letting delta x approach 0 in the difference quotient for the secant line, we get closer and closer to point P with coordinates x0, f of x0. By doing so, we get better and more accurate approximations to the slope of the tangent line passing through P, as we can see in figure 2. Therefore, we have that the slope of the tangent line is the limit as delta x approaches 0, of f of x0 plus delta x, minus f of x0, all over delta x, labeled as 10.1. The above limit is called the derivative of f at x0, and is denoted as f prime at x0, or dy dx evaluated at x0. We refer to this as the difference quotient definition of the derivative. In general, a function f is said to be differentiable at x if its derivative exists at x. Moreover, f is differentiable over an open interval ab, if its derivative exists at any point in ab. Now, let's examine an application of the derivative from Newtonian physics, namely, instantaneous velocity. Consider an object moving in a straight line described by its equation of motion, x equal to f of t. Here, x is the displacement of the object from the origin at time t. Also, f of t is called the position function of the object. So, in the interval from t0 to t0 plus delta t, the change in position delta x equals f of t0 plus delta t, minus f of t0 in figure 3. Thus, the average velocity of the object is given by f of t0 plus delta t, minus f of t0, all over delta t, which equals delta x over delta t. Note that this is the slope of the line between the points P and Q in figure 4. But what is the instantaneous velocity of the object at any time t equal to t0? We set out to answer this question next. Continuing with instantaneous velocity as our application of the derivative, consider computing the average velocities over much shorter time intervals, from t0 to t0 plus delta t. So now we let delta t approach 0 in the formula we obtained for the average velocity. Therefore, the instantaneous velocity of an object at any time t equal to t0, is v of t0, which is the limit as delta t approaches 0, of delta x over delta t. This is equal to the slope of the tangent line at the point P in figure 5, and hence, the derivative of the position function at time t equal to t0, which is given by dx dt evaluated at t0, or equivalently, f prime at t0. Here are several math applications of the derivative. Topics such as rates of change and related rates, critical points, and maximum or minimum values of functions, first and second derivative tests, Rolle's theorem and the mean value theorem, implicit differentiation, and L'Hopital's rule are typically dealt with in the beginning of a course introducing differential calculus. Usually, Newton's method and linear approximation with Taylor and Maclaurin series are studied later, or in the second course in a calculus class sequence. The topics of differentials, partial derivatives, optimization, and ordinary and partial differential equations are often covered in a multivariable calculus course. We may consider some of these topics in future videos, so stay tuned. A few of these topics were covered in previous videos. For instance, critical points of functions were discussed in the problem 1 video, the Lagrange multiplier method, which involves partial derivatives and optimization, was the topic of problem 3, and approximation with Taylor series was dealt with in problem 5 from the viewpoint of complex analysis. Also, ordinary differential equations were the subject of the video for problem 8. Here are a bunch of real-world applications of the derivative. We already talked about instantaneous velocity as an application from Newtonian physics. Another one is instantaneous acceleration, which is defined as the derivative of the velocity with respect to time t, or equivalently, the second derivative of the position with respect to time t. Other such applications include momentum and Newton's second law of motion. Additional applications may vary, such as astrophysics, electromagnetism, optics, classical mechanics, and quantum mechanics, among others. The derivative also applies in areas of biology, chemistry, archaeology, and the earth sciences, such as population growth and decay, carbon dating, atomic theory, seismology, and climate change, for instance. In terms of economics, business, and finance, the derivative is applied in areas such as profit and loss, business growth, interest rates, financial data analysis, stock prices, and risk management, for example. Other areas where the derivative may be applied include, but are not limited to, engineering, architecture, robotics, animation, and machine learning. Now, we will look at the history behind the derivative. According to reference 1, the derivative was first used, it was then discovered, it was then explored and developed, and it was finally defined. I will explain more about this subsequently. Typically, much of the history of the derivative is known from the context of European mathematics, but power series representations of functions, studied in differential calculus, may have developed earlier than in 17th century Europe. In fact, Power series for the sine, cosine, and arctangent functions were approximated and developed in the Kerala School of Astronomy and Mathematics in South India, founded by Madhav, which flourished from the 14th to the 16th century, as per reference 5. Its primary focus was on trigonometry and circle geometry to help astronomers calculate positions of stars and predict astronomical events, which were important in scheduling Indian religious holidays. Thus, the search for more accurate approximations was a constant quest. The Kerala school approximated pi and circumference values to a level of such accuracy that it inspired the interest of mathematicians in series approximations, including power series and infinite series expansions. However, it's still unclear whether the use of series at the Kerala school had any impact on the development of the derivative in European mathematics at the time. So, Madhav founded the Kerala school, but the concept of the derivative likely originated from the study of tangent lines in ancient Greece, as in reference 4. Now, the derivative is a fundamental concept in differential calculus. In fact, the word calculus is Latin for small pebble, and since pebbles were used to compute distances, tally votes, and do abacus arithmetic, the term came to mean a method of computation in ancient times, as per reference 2. In the ancient world, areas and volumes of objects were also studied and investigated. The 5 Platonic solids, for instance, were named after Plato from ancient Greece. Centuries later, the study of areas would become the precursor of the concept of the integral, studied in what is known as integral calculus. Math advanced further with the founding of the Hindu-Arabic numeral system and algebra in the Islamic world, as per reference 3. Following the advancement of culture and the arts due to the Renaissance, by the 16th to 17th century, European mathematicians invented symbolic algebra, founded by François Viète in 1591, and analytic geometry, founded by René Descartes and Pierre de Fermat, in the 1630s. Fermat developed a method of finding maxima and minima, referred to as extrema, based on work by Pappus, according to reference 1. Continuing our discussion of the history of the derivative, this method led Fermat, along with Descartes, John Wallis, Isaac Barrow, and others to study the tangent to a curve y equal to f of x, through considering and computing the secant, given by the ratio f of x plus h, minus f of x, all over h, where h is a constant. By about 1660, it was understood that a maximum was found by calculating the slope of the tangent and setting it to 0. The immediate motivation for the concept of the derivative did not actually come from physics, though we saw some applications of the derivative to various areas of physics. In fact, the concept developed from mathematical geometry and gradually evolved in conjunction with the ideas of extrema, tangent, area, limit, continuity, and function, as in reference 1. Now, it is known that Isaac Newton and Gottfried Leibniz invented the calculus independently in the 1660s. They both culminated ideas of extrema, tangents, and areas into the concepts of derivative and integral, according to reference 1. They created their own notation as well. For example, Newton used a dot on top of x, to indicate the first derivative of the position function for an object at time t, which is its instantaneous velocity, or, what we also refer to as x prime. Leibniz used dy dx to represent the derivative of a function y with respect to x, and he used an S-shaped symbol, today known as the integral sign, followed by y dx to denote the integral of a function y with respect to x. They also gave arguments to prove the fundamental theorem of calculus 2. Newton called the derivative a fluxion, while Leibniz referred to it as a differential quotient. Their contributions to calculus were profound but also met with skepticism and even ridicule. Nevertheless, Newton's laws of motion, for example, in physics would be translated into the context of the derivative. In particular, the second law of motion is written as the equation F equals m times x double prime, where F represents the force on an object, m its mass, and x double prime its acceleration. Continuing with our discussion of the history of the derivative, Hooke's law of elasticity, named after the 17th century British physicist Robert Hooke, stated that the force required to stretch or compress a spring by a given distance is proportional to that distance. Mathematically, this is expressed as F equals negative kx, where F is the force applied to the spring, k is called the spring or elasticity constant, and x is the displacement of the spring. Equating it with Newton's second law, Leonhard Euler solved the ordinary differential equation mx double prime plus kx equal to 0 in 1739 for the motion of a vibrating string, based on reference 1. Mathematicians such as John D'Alembert, Daniel Bernoulli, and Euler also analyzed solutions to the partial differential equation given by the second partial derivative of y with respect to t, equal to capital T over rho, times the second partial derivative of y with respect to x, known as the one-dimensional wave equation, again modeling the motion of a vibrating string. Here, y is an unknown function in two variables x for space and t for time, representing a deflection, or the displacement, of the string. Capital T is the tension on the string, and rho is the mass per unit length of the string. In fact, Brooke Taylor had used related ideas to create his Taylor series for functions, a while earlier. Joseph-Louis Lagrange considered the derivative as a function f prime of x, calling it a derived function, and he also nearly obtained the epsilon delta definition for the derivative of a function, according to reference 1. By the early 19th century, Augustin Louis Cauchy defined the derivative of f of x as the limit, when it exists, of the quotient f of x plus h, minus f of x all over h, as h approaches 0. He also expanded on the epsilon delta definition. We are now at the last part of our discussion of the history of the derivative. From where we left off, in 1850, the mathematician Karl Weierstrass gave lectures on the derivative at the University of Berlin, defining it by using his own algebraic methods and the distinction between pointwise and uniform convergence of functions, combined with Cauchy's epsilon delta techniques. His ideas were disseminated by his students, such as Schwarz, Mittag-Leffler, Kovalevskaya, and Cantor, to the mathematical centers of Europe, as per reference 1. Remember that with respect to the derivative in Europe, according to reference 1, it was first used, it was then discovered, it was then explored and developed, and it was finally defined. More specifically, Fermat implicitly used it, Newton and Leibniz discovered it, Taylor and Euler developed it, Lagrange named and characterized it, and finally, Cauchy and Weierstrass rigorously defined it. This concludes our discussion of the history of the derivative. We are now ready to solve problem 10, but we will need some quick facts and review before doing so. Let's begin with the first set of quick facts and review we will need for problem 10. Without loss of generality, setting x not to x, and delta x to h, we may rewrite 10.1 as f prime of x, equal to the limit as h approaches 0, of f of x plus h minus f of x, all over h, labeling it as 10.2. We may now refer to 10.2 as the first derivative of f at, or with respect to, x. Since the function y equals f of x, we can sometimes write f prime of x as y prime, in the notation of Lagrange, dy dx, in the notation of Leibniz, dxf, in the notation of Euler, or y with a single dot on top, in the notation of Newton. Higher derivatives of f at, or with respect to, x, can be written similarly. For all intents and purposes, unless otherwise specified, we shall stick with the Lagrange and Leibniz derivative notation, interchangeably, in this video. In this second set of quick facts and review for problem 10, for the derivative rules of functions that are to follow, we shall assume the functions to be real valued in the variable x and well defined over their domains. The constant rule states that the derivative of any constant is always 0. The constant multiple rule states that the derivative of the product of a constant and a function f equals the product of the constant times the derivative of f. The sum or difference rule states that the derivative of the sum or difference of two functions f and g equals the sum or difference of the derivative of f and the derivative of g. The power rule states that the derivative of the function x to the power n, for any integer or real number n, equals n times x to the power n minus 1. The product rule states that the derivative of the product of two functions f and g equals the sum of the derivative of f times g and f times the derivative of g. The quotient rule states that for two functions f and g, where g is not equal to 0, the derivative of the quotient f over g equals the derivative of f times g minus f times the derivative of g, all over g squared. Finally, the chain rule states that for two functions f and g, the derivative of the composition f of g of x equals the derivative of f at g of x, times the derivative of g at x. In this last set of quick facts and review, we have derivative formulas for various real-valued functions in the variable x. These include exponential, logarithmic, trigonometric, inverse trigonometric, and hyperbolic functions. We won't really need these for problem 10, but we may refer to them in future videos, so stay tuned. Let's proceed to solve problem 10. For part A, the infinite power series expansion about 0 for the natural exponential function e to the power x, is given by the sum from n equals 0 to infinity, of x to the power n, all over n factorial. Using the difference quotient definition of the derivative, we have that the derivative with respect to x, of e to the power x equals the limit as h approaches 0, of e to the power x plus h, minus e to the power x, all over h. Using the properties of exponents, we can factor out e to the power x in the numerator of the expression to the right of the limit sign, as we have here. Moreover, since the limit depends only on h and not the variable x, we can pull e to the power x out in front of the limit sign. After some basic algebra, the entire expression becomes e to the power x, times the limit as h approaches 0, of 1 plus h over 2 factorial, plus h squared over 3 factorial, and so on and so forth. Finally, this simplifies to e to the power x times 1, which equals e to the power x, as needed. In part B of problem 10, we are given the function f of x equal to 1/3, x cubed, plus 1/2 x squared, plus x. We must find its derivative f prime of x. Using the constant multiple rule, sum rule, and power rule for derivatives, we have f prime of x equal to 1/3, times the derivative with respect to x, of x cubed, plus 1/2 times the derivative with respect to x, of x squared, plus the derivative with respect to x, of x. This equals 1/3, times 3x squared, plus 1/2 times 2x, plus 1. This simplifies to a final answer of f prime of x equal to x squared, plus x plus 1. In part C, we have the function g of x equal to 2x cubed minus 3, all over x plus 2, where x does not equal negative 2. Let the function g1 of x equal 2x cubed minus 3, and g2 of x equal x plus 2. With that, we may now write g of x as the quotient g1 of x, over g2 of x, where x does not equal negative 2. Using the quotient rule for derivatives, we must find g prime of x, which we will do next. Continuing with part C, by the quotient rule for derivatives, we have that g prime of x equals g1 prime of x, times g2 of x, minus g1 of x, times g2 prime of x, all over g2 of x squared. Note that by the power rule for derivatives, g1 prime of x equals 6x squared, and g2 prime of x equals 1. Using this information, along with doing some basic algebra and simplification, we obtain a final answer of g prime of x equal to 4x cubed, plus 12x squared plus 3, all over x plus 2 whole squared, where x is not equal to -2. In part D, we have the function h of x, equal to the square root of 1 minus x cubed, where x is less than or equal to 1. Let h1 of x equal the square root of x, where x is positive, and h2 of x equal 1 minus x cubed, which is defined for all real values of x. Note that we can write h of x as 1 minus x cubed, to the power 1/2, and h1 of x as x, to the power 1/2. Furthermore, we have h of x equal to, the composition h1 of h2 of x. So, we must use the chain rule for derivatives, to calculate the derivative h prime of x. Continuing with part D, using the power rule for derivatives, h1 prime of x equals 1/2, times x to the power -1/2, or 1, over 2 times the square root of x, which is defined for all strictly positive real values of x. Also, h2 prime of x equals -3x squared, which is defined for all real values of x. Using this information, by the chain rule for derivatives, h prime of x equals h1 prime of h2 of x, times h2 prime of x. But this equals h1 prime of 1 minus x cubed, times -3x squared, and this equals 1/2, times 1 minus x cubed to the power -1/2, times -3x squared. Simplifying further, we get a final answer of h prime of x equal to -3x squared, over 2 times the square root of 1 minus x cubed, where x is less than 1. This concludes our video for problem 10. I hope you liked it. If so, be sure to subscribe to this channel. Thank you for watching.